are studying the dynamics of systems in transform domain. In the previous week, we came across a situation where we try to understand the step response of a system having two tanks, and we considered two cases. In one case where the two tanks were non-interacting, we got a second order transfer function where the denominator of the system of where the denominator of the transfer function rather was a second degree polynomial. Whereas, in the second case, when the transfer function when the systems were interacting, then the transfer function had a first order polynomial in a first degree polynomial in the numerator and second degree polynomial in the denominator. Now, following the conventional definition, we identify the order of a system from the degree of the polynomial of the denominator of our transfer function. Here, when you have a first degree polynomial in the numerator and a second degree polynomial in the denominator, the question of the order of the system becomes a little tricky, and we need to have a little different definition. So, that particular concept gives rise to the PQ order systems, which we are going to study today. So, today's lecture will involve the analysis of PQ order systems. But before we understand the meaning of a PQ order system and associated dynamics, let us consider one specific example from a physical system. Now, this is a system where you have a mixing tank and you have two streams coming in the tank, mixing takes place, and then you have one stream going out of the tank. Okay. So, let us look at the system and various assumptions which we can make about the system. So, we have a tank which is a mixing tank. So, it would be equipped with a stirrer, and you have two inlet streams. The first stream on the left hand side gives you the feed as A with a volumetric corresponding volumetric flow rate of F A, and similarly on the right hand side you feed B and the corresponding volumetric flow rate of B is F B. There is certain level of the liquid which would be maintained in the mixing tank, and at the outlet you have an arrangement such that a part of your inlet stream B can be bypassed. So, this is a bypass. Okay. So, now we are mixing A and B. So, for this particular problem we would be tracing the concentration of B. Okay. So, let the concentration of B in the tank be C B tank. This is the concentration of B inside the mixing tank. We would assume a constant volume of the system. So, we would have the notation V, which denotes the constant volume of the liquid inside the tank. Now, I have a situation where a fraction of my inlet stream B goes to the tank and the rest is passed as a bypass directly to the outlet of the system. So, let us say R, which is a fraction of what goes of what is fed as F B, is sent as a bypass, and therefore, 1 minus R would go to the tank. Okay. Further, what we can say is that the concentration of the species B in the feed is C B F. F stands for feed. Okay. Is there anything else which we would need to specify? Yes. What we also need to specify is that out of the tank there is a stream which is coming out, and the outlet from the tank has a volumetric flow rate F out. So, F out is what is coming out of the tank, okay. And you have a junction, let us say the junction J here, the outlet from the tank. So, the material which is coming out of the tank after mixing and the bypass, they meet at the junction J, and therefore, the concentration of the species B downstream to J would be different, and let me call that as C B out. Let me call that as C B out. Okay. So, now I need to do the analysis of the dynamics of this system. Okay. Before we do that, do this analysis, let us make some assumptions. Okay. So, first assumption that I make is that F A, the volumetric flow rate of A, is very large compared to the volumetric flow rate of B. F A is very large compared to F B. First assumption, and then you see that I have not written any densities anywhere in my system, either on the figure which is given on the left hand side or the figure which I have drawn on the right hand side. So, this obviously should give you an idea that you have a constant density system, but before I do that, let me say that the density is rho A of the stream which is coming from the left hand side, density is rho B of the stream which is coming from the right hand side. Then you have rho tank, which will be equal to rho tank here, and then after mixing takes place in junction, you have rho out. Okay. This is these are the details, but then what we can assume is here that all of the densities are similar. We cannot say that the densities are same, but the densities are similar. So, therefore, rho A is similar to rho B, which is similar to rho tank, which is similar to rho out. This is another assumption that I have made. Now, based on this diagram and these assumptions, I can now develop my model equations, which I would like to use for the analysis of my system. So, let us quickly try to write the model equations. Very quickly, the diagram is like this. C B tank, V rho's, the densities are constant everywhere, and let us call that as rho simply. So, I have here F A, here F B, C B feed, a part of that goes as the bypass. So, this is 1 minus R, this is C B out. Okay. So, if this is my system, I can do one overall mass balance. Okay. So, I can write overall mass balance over the tank. So, overall mass balance over the tank. What it would give me? Densities are constant everywhere. So, I can write the time rate of change of V dV by dt multiplied by rho, density is a constant, is equal to F A rho plus 1 minus R rho F B minus this was written as F out times rho, right. So, this is the overall mass balance for the streams which are coming in and going out. Okay. Rho is constant throughout, so it will get cancelled, and for F A very large compared to F B, I can write this, and constant V is equal to constant. These are the assumptions which I have made. I can write this, that F A is equal to F out. Okay. So, very small amount of B is entering as the inlet flow rate of B. So, therefore, essentially the outlet from the tank is equal to the inlet of A. This is what this equation means. So, equation 1. Now, I can write the overall mass balance at the junction J. So, this is the junction J, right. I can write this overall mass balance at the junction J, and this would be equal to what? Rho times d V by dt, and this is the volume of the junction, and junction has no volume. So, this term will become equal to 0. This is equal to F out times rho plus R times F B rho minus rho F outlet. F outlet is here, F outlet, the ultimate flow rate out of the system, and from here I know that F out is equal to F A, and F A is much larger than F B. Therefore, I can write, and considering the volume of the junction as practically 0, I can write F A is equal to F out is equal to F outlet. Okay. So, this is my equation 2, and these two equations have come from overall mass balance. Now, I can do a similar component balance. So, let me write the component balance. Component balance over the tank. Okay. My system is this, I have a constant volume, I have C B tank, F A, junction J. So, what would be the concentration of B coming out of the tank? This would be simply C B tank, right. What would be the flow rate from the overall mass balance? Mass balance, I have established that this would be equal to F A, which is equal to F out, right. Now, I have F B C B feed, this is R, this is 1 minus R, and this is C B out, and this is F A, which is equal to F A outlet. This is also I established. So, let me make the component balance over the tank for B, right. So, the time rate of change of B in the tank will be given as, for constant volume, V d C B tank by dt, dCB tank by dt is equal to, from stream A no B is coming, from stream B, B is coming at a concentration of CBF, but only fraction 1 minus R is going there. So, therefore, I can write this as 1 minus R F B. This would be the volumetric flow rate multiplied by the concentration. So, C B F. This is the amount of B which is coming in the tank, and what is leaving out of the tank would be minus of the concentration of B in the at the outlet of the coming out of the tank is simply C B tank, and the flow rate is F A. So, this would be F A multiplied by C B tank. Fine. So, what I see from here is that I have a dynamical equation in which my dynamical variable is C B tank, and if I have understood the method of doing a transfer function analysis, that then I can rearrange this equation to a suitable form. So, let me do that rearrangement. I can write this as V d C B tank by dt plus F A C B tank is equal to 1 minus R F B C B feed, and to have the transfer function we would convert it to a standard form, and this would be equal to V upon F A d C B tank by dt plus C B tank is equal to 1 minus R multiplied by F B C B feed upon F A. Now, equation 1 seems to be in a standard form, because I have d C B tank by dt with some coefficient plus C B tank with coefficient unity, which is of the form tau dy by dt plus y is equal to, now on the right hand side I have 1 minus R F B C B feed by F A, which means I have on the right hand side k times u, where u is the input function for the system and F C B F upon F A can be identified as the term u, right. Can I write anything more? Well, in the previous overall mass balance, I wrote the overall mass balance around the tank and also at the junction. Let me do the component balance. So, component balance at the junction. Okay. So, at the junction you have the inlet which is coming, which is the outlet from the tank. So, therefore, I can write this as F out, and F out is equal to F A. So, F A multiplied by C B tank plus from the other side the fraction of the stream from F B, which is the bypass stream, is coming. So, therefore, this would be R times F B, and concentration of B there is C B feed, and this must be equal to the outlet, what is going on at the outlet, and at the outlet F A outlet is equal to F A. So, I can write this as F A multiplied by C B out, from where I can write C B out is equal to C B tank plus R multiplied by F B C B F divided by F A, equation number 2. So, let me try to understand what do equations 1 and 2 give me. Equation 1 gives me, equation 1 is a dynamical equation. It gives me how does the concentration of B inside the tank change as I change the volume, as I change the flow rates, as I change the feed concentration of B in the stream B, and also the ratio of or the fraction which goes to the tank and one which goes to the bypass. But now, my ultimate output from the system is C B out, because I am mixing the two streams at this junction J. So, therefore, my ultimate outlet is C B out, and how do I get C B out? I get C B out from equation number 2, which is nothing but the concentration which is coming from the tank plus the effect of the stream which is coming directly to the junction. Okay. Now, let me do one thing. Since I have put the two equations in a standard form, let me try to do a transfer function analysis, and if I do that, I would prefer my system to be in deviation variable form. So, therefore, I say that I now declare that let us say that C B tank minus C B tank at steady state is a variable x. Okay. Then I say that C B out minus C B out at steady state is a variable called y. Y is the output variable. If you remember long back, we actually did this analysis in state space domain, and we said that we can have dynamical variable and we can also have the specification of output variable. So, in this particular case, it is not difficult to find out that y is your output variable, and then on the right hand side of equations 1 and 2, I see F B, C B F, F by F A. All of these would act as the input functions. So, therefore, let me call F B C B F upon F A minus the same quantity at steady state F B C B F upon F A steady state is equal to u. If this is the case, then I can write equation 1 as V over F A dx by dt plus x is equal to 1 minus r u, equation number 3, and y is equal to x plus r times u, equation number 4. So, now I have two equations in the deviation variable form, and then let me try to determine the transfer function of the system. So, this is V by F A. So, let me call this as V by F A dx by dt plus x is equal to 1 minus r times u, say equation number 1, and y is equal to x plus r times u, equation number 2. So, when I have equations of this form, what do I do? Well, I can take the Laplace transform on both the sides. So, from equation number 1, I can get v upon f a s plus 1 of x bar of s is equal to 1 minus r u bar of s, from where I can simply write x bar of s divided by u bar of s is equal to 1 minus r upon v by f a s plus 1. Is this a transfer function? Well, yes, it is a transfer function, but what kind of transfer function is this? What information does it give to us? This is x bar upon u bar. So, this means that this transfer function gives us the dynamics of the system when you are tracing the change in the concentration of B in the tank. So, you have here C B tank, right. So, as you change C B, as you change the variables of u, which involves C B feed F B upon F A, how does C B tank change? What is the response of C B tank? This is what this transfer function gives us. But then you also had this here C B out. You would like to know, if I change various quantities in the input function, how does the ultimate concentration out of the system change? Well, that can be obtained by doing the transfer function analysis from equation number 2. So, I can write y bar of s is equal to x bar of s plus r times u bar of s, from where I can write y bar of s upon u bar of s is equal to x bar of s upon u bar of s plus r, and from equation number 3 I can write x bar of s upon u bar of s as 1 minus r upon v by f a s plus 1 plus r, right, and this is equal to what? So, y bar of s upon u bar of s is equal to 1 minus r plus v r upon f a times s plus r divided by v upon f a s plus 1, from where I can write y bar of s upon u bar of s as v r upon f a times s plus 1 divided by v upon f a s plus 1, and let me call this equation number 4. And if I look at the transfer function given in equation number 4, what I see is that I have y bar, which means the ultimate output, the outlet concentration from the system divided by the input to the system. So, therefore, now you can, instead of having an indirect idea of how does the concentration change inside the tank and then how does it affect the outlet, you can have an idea directly as how does the outlet concentration change as a function of different quantities in the input, and that is given by transfer function of equation 4. But lastly, what we can see is that if I declare V by F A as a quantity, and I told that this seems to be the time constant of the system. So, if I declare it as a constant quantity tau, then in the numerator I have some different quantity, and let me call V R by F A as zeta. And if that is the case, then I can write y bar of s upon u bar of s is equal to zeta s plus 1 upon tau s plus 1, equation number 5. And let us compare equation number 5 with equation number 3. So, I have x bar of s upon u bar of s, and this is equal to 1 minus r divided by tau s plus 1. This was equation number 3. So, now I need to ask this question that can I comment upon the dynamics of the system? Well, I have two variables which I can identify in the system. If I am tracing the dynamical response of my system for the change in the concentration of B inside the tank, then from equation 3 it is quite simply a first order system, okay? Because 1 minus r can be identified as the static gain of the system, tau the time constant of the system is V by F A, first order dynamics. But what I see from the dynamical response of the outlet concentration as a function of various input quantities, then I have the transfer function as zeta s plus 1 divided by tau s plus 1, one polynomial of degree 1 in the numerator and one polynomial of degree 1 in the denominator. It is not a simple first order transfer function, and therefore, we declare such transfer function as or such system as 1 order system. What is the meaning of 1 order? 1, the first one stands for the degree of the denominator and the second one stands for the degree of the numerator. So, therefore, a PQ order system is a system which has a transfer function in which the degree of the denominator is P and the degree of the numerator is Q. The order of the numerator, the denominator and the numerator as P and Q must be taken care of. So, now we understand that we can have situations where different polynomials of different degrees can in fact appear in the numerator as well as the denominator of the transfer function. What we would like now to know is the dynamical response of such systems. In other words, what would be the effect of adding a term in the denominator, what would be the effect of adding a term in the numerator, and so on. We will take this particular concept in the next lecture. Till then, goodbye.